Hey guys, welcome back. The last couple of lessons we have talked about ionic bonds. So at this point, we know how to determine ionic compound formulas as well as name ionic bonds, whether they have transition metals or not. So we should know how to do that. Also, we need to know how to determine formulas and the names of polyatomic ions. So any of those ionic bonds that have the polyatomics. Today we are going to continue our lessons on bonding by talking about metallic bonds. Now this is going to be a lot easier than the ionic bonds, so just stick with me and we'll get through it together. All right, so just to review, this stuff you have already heard already because we've done metals, nonmetals, and metalloids, so this should be just a brief review for us. But just to remember, or a reminder, metals are solid material that are typically hard, shiny, malleable, meaning that they can be molded and take the shape of whatever you mold them into. Fusible and ductile. Remember, ductility is the ability to be molded into a wire. They're good electrical and thermal conductors, so we use them to conduct heat and electricity. Iron, gold, silver, copper, aluminum would all be examples of metals. And we, of course, know that our metals are on the left-hand side of the periodic table. Ductility just means being stretched without getting damaged. So examples of this would be like copper wire. Copper is very ductile. We use it in copper wiring. Malleability is the ability to be hammered or pressed without breaking. You guys are pretty young. I don't know if you or your parents were ever fans of MC Hammer, but the MC Hammer pants were a big thing back in the day. And then this is just an image of a metallic bond, what it would look like on the molecular level. And we're going to take a look at this here in just a second. So what is a metallic bond? This is just the force of attraction between valence electrons and their metal ions. Metals will have high melting points and boiling points, which suggests that these bonds are very strong. So remember, in an ionic bond where you have a metal and a nonmetal, those valence electrons are transferred from the metal to the nonmetal. Remember, our metals, they have anywhere from 1 to 3, 4 valence electrons, and they're wanting to kick them off. They want to get rid of them, right? So they're wanting to get rid of those electrons. Well, here in a metallic bond, these are occurring between one or more metals. So it can either be the same metal, that there's lots of atoms of that metal, or a compound of metals. Now, when this happens, you have your cation, which is your metal, right? So your elemental metal, and then you have all of these valence electrons around it. Now, these are a sea of electron. They don't really have a high affinity for their atoms. So instead of being attached to one single atom of the metal or the metal compound, they kind of just exist as like a sea of electrons. So they exist and they kind of are, what's a good way to put this? Kind of just amorphous almost. They can go between the different atoms and they exist in different places. So a reminder just about conductivity. Metals are good conductors of heat and electricity. This is because the valence electrons are delocalized. So they're not actually attached to the cation. So they're able to carry that heat or the electrical energy around the structure. Again, this is like a sea of electrons. They're not really committed to one specific atom. So these electrons, because they're free and they're delocalized, they can spread that heat and that electricity. And of course, we know that our metals are malleable and ductile. This is also because of the structure of these metallic bonds. So again, those cations, they're not firmly attached to the electrons or each other. And this allows the cations and the electrons to move around while still maintaining the chemical structure. That's why we're able to, mold gold or silver into jewelry and it keeps its shape. That's why we're able to create copper wires, that ductility, because since they're not firmly bound together, it's easy to manipulate the structure and it will keep its overall shape because the chemical structure is not going to be messed up, but because these electrons and their cations are not firmly held together, they are malleable and they can be moved around. Now, let's talk about naming metallic compounds, because you guys know there's special ways to name ionic compounds, especially if there are polyatomics or transition metals involved. For metallic compounds, there's no special naming. You either use the name of the element or a common name. So there's no special rules for naming metallic compounds. You don't have to worry about naming it. So is it gold? Oh, it's gold. Is it silver? It's silver. If there's like some kind of compound, it could be a metal alloy. It would have a special name, but you guys don't have to remember anything. The biggest thing that you have to know about metallic bonds is just that metallic bonds occur between either one or more types of metals. So you're never going to see a non-metal in a metallic bond. So these are metals only. So ionic bonds are metals and non-metals. Metallic bonds are metals only. And because of the bonds between these metals, that's why we get the composition of metals in terms of their characteristics of their ductility and their malleability. So remember, those electrons don't have a high affinity for their cations, so they're just existing kind of as a sea of electrons, which are allowing that heat and that electrical transfer. Okay, and that's it. Really, the most that we'll need to know is be able to look at two elements and say, oh, these are two metals. They're going to form a metallic bond. Metals are shiny. They're good conductors of electricity. They are malleable and they are ductile. They have a high luster. If you can tell me that, you'll be A-okay for this unit.